The object's journey through our solar system was brief, but its story is eternal. It didn't land, didn't speak, didn't linger, yet it spoke volumes through its existence, proving that intelligence, be it machine, life, or both, thrives beyond our world. It showed us that the universe is not a void but a tapestry woven with purpose and mystery. As we analyze its data, build new technologies, and dream of distant stars, we carry its legacy forward. This visitor was a spark, igniting a fire of curiosity and unity. It reminded us that we're not just inhabitants of a pale blue dot, but participants in a cosmic saga. So, what's next? Will we chase this mystery, sending our own probes to the stars? Will we decode its signals, unlocking secrets of a distant civilization? Or will we simply marvel, letting its presence inspire us to be better, bolder, wiser? Share your thoughts in the comments, and let's keep this cosmic conversation alive. If this story stirred your soul, give it a like and share it with someone who gazes at the stars. The universe is calling. Let's answer together. Imagine peering back in time to a universe just a few 100 million years old. That's what the JWST does, capturing light that's traveled for over 13 billion years to reach us. Scientists expected to see a proto-universe, a scattering of small, dim galaxies, the first tentative steps of cosmic evolution. But what they saw was anything but tentative. The early universe was alive with galaxies, far more than our models predicted. These weren't just faint glows, they were dazzling, packed with stars that seemed to have formed far too quickly. And at the centers of these galaxies lurked supermassive black holes, monstrous giants with masses billions of times that of our sun. How could such massive objects exist so early? Our understanding of the universe was unraveling, and the stakes couldn't be higher. If you're intrigued, drop a comment below. Have you ever wondered how the universe got its start? The problem wasn't just the number of galaxies, it was their brightness. According to our cosmological models, forming stars takes time. Interstellar gas and dust must slowly gather under gravity's gentle pull until enough mass accumulates to ignite a star. Those stars live, die, and give birth to new ones, a process that spans millions, even billions of years. Yet the JWST showed galaxies so bright they implied an impossible number of stars, formed far too fast. Cosmologists were stunned. Some even declared a crisis in cosmology, as if the universe itself was mocking our carefully crafted theories. But as the data poured in, a glimmer of hope emerged, a clue that might explain the unexplainable. Enter the black holes. Scientists at the University of Texas, studying the JWST's Cosmic Evolution Early Release Survey, proposed a bold idea. What if the excess brightness wasn't from stars alone? What if massive black holes, lurking at the hearts of these early galaxies, were stealing the show? These cosmic titans, surrounded by swirling accretion disks of gas and dust, generate intense friction as they feed. That friction produces light, blinding, brilliant light that can outshine entire galaxies. If these black holes were gobbling up matter at a ferocious pace, their accretion disks could account for the extra glow, reducing the need for an implausible number of stars. Suddenly, the galaxy's masses fell back in line with our models. Problem solved, or so it seemed. This discovery was a game changer, reinforcing how crucial black holes are to understanding the early universe. But it also opened a new can of worms. While the brightness issue was resolved, the black holes themselves posed a bigger question. How did they get so massive so fast? Small, stellar black holes, formed from the collapsed cores of massive stars, are no mystery. With masses a few to 100 times that of our sun, they fit neatly into our timeline of the early universe. But supermassive black holes, weighing tens of thousands to billions of solar masses, are a different beast. According to a principle called the Eddington limit, they shouldn't have had time to grow that big. Yet, there they were, defying our expectations like cosmic outlaws. If this twist has you hooked, hit that subscribe button to join our journey through the stars. To understand this puzzle, let's talk about the Eddington limit, a concept first formulated by English astronomer Arthur Eddington in 1920. Picture a black hole as a ravenous diner, pulling in gas and dust with its immense gravity. As this material spirals into the black hole's accretion disk, it heats up, emitting photons, particles of light that carry momentum. These photons push outward, creating a kind of cosmic wind that resists the inflow of matter. At a certain point, the brightness of the accretion disk becomes so intense that its its outward push balances the black hole's gravitational pull. This is the Eddington limit, the maximum rate at which a black hole, or a star, can consume matter without blowing its meal away. For stars, brushing against this limit is dangerous. Take Wolf-Rayet stars, massive beasts 20 times heavier than our sun, radiating powerful stellar winds. They're so bright they're on the verge of tearing themselves apart. Black holes, despite their reputation for swallowing light, face a similar constraint. Their accretion disks can shine brighter than entire galaxies, and that brightness limits how fast they can feed. In theory, a stellar black hole could grow into a supermassive one by consuming matter over time, but simulations show this would require near constant feeding at the Eddington limit from the moment of the black hole's birth. An unlikely scenario, as black holes often run out of nearby material and must wait for more to drift close. Here's where things get weirder. Supermassive black holes, common at the centers of galaxies, don't seem to have an intermediate stage. You'd expect to see a spectrum of black holes, small stellar ones, medium-sized ones, and supermassive ones, as they grow over time. But intermediate black holes are curiously absent. In our Milky Way alone, astronomers estimate there are 100 million stellar black holes, yet only a handful of potential intermediate candidates have been spotted. This gap raises a tantalizing question. Are supermassive black holes even grown-up stellar black holes, or do they form in a completely different way? Some scientists propose a radical alternative, direct collapse black holes. In the dense, chaotic early universe, where matter was packed tightly together, vast clouds of interstellar dust might have collapsed directly into massive black holes, bypassing the star stage entirely. This theory suggests supermassive black holes could have been born big, ready to dominate their galaxies from the start. It's a compelling idea, supported by some evidence, but far from certain. The universe, it seems, is keeping its secrets close. If you're loving this cosmic detective story, share your thoughts in the comments. What do you think black holes are hiding? Just when scientists thought they were closing in on answers, a new player entered the scene, LID 568, a black hole so distant it's 12.1 to 12.3 billion light years away. Its light, redshifted into the infrared by the universe's expansion, is too faint for even the mighty Hubble Space Telescope to detect alone. It took the combined power of the Chandra Cosmos Legacy Survey and the JWST's unparalleled resolution to spot this faint red dot of a galaxy. But what LID 568 revealed was nothing short of astonishing. It's breaking the Eddington limit, and not just by a little. This black hole is consuming matter at 40 times the supposed maximum rate, like a cosmic speeder tearing through a galactic speed trap. How can this be? The Eddington limit isn't absolute, it turns out. Black holes can cheat it in short bursts or through clever tricks. For instance, some black holes channel their energy into powerful jets, blasting photons in a single direction. This leaves other directions free for matter to spiral in unhindered, sidestepping the limit. Alternatively, a greedy black hole might snatch extra matter in a fleeting feeding frenzy before the accretion disk's brightness pushes it away. LID 568 is the clearest example yet of a black hole in super-Eddington mode, gobbling up matter at a rate that could explain how supermassive black holes grew so quickly in the early universe. LID 568's existence is a game changer. It proves that black holes can exceed the Eddington limit, offering a potential solution to the supermassive black hole mystery. But the puzzle is far from solved. Why are intermediate black holes so rare? Why were there so many galaxies in the early universe, more than our models allow? Do direct collapse black holes really exist? Or is LID 568 super-Eddington feeding the key to everything? These questions linger like shadows in the cosmic void, challenging our understanding of the universe's infancy. The JWST has given us a front row seat to billions of trillions of stars, a flood of data that's both a treasure and a challenge. Like a black hole approaching the Eddington limit, we risk being overwhelmed if we try to absorb it all at once. Yet each new discovery, like LID 568, brings us closer to unraveling the universe's deepest secrets. Cosmos is a master storyteller, revealing its plot twists one photon at a time. If this journey has sparked your curiosity, hit that like button and share this video with a friend. Let's spread the wonder of the universe together. As we marvel at these cosmic revelations, it's worth noting the human effort behind them. Recent reports indicate that NASA has faced significant challenges, with nearly 4,000 employees leaving due to budget cuts as of August 17, 2025. This loss is a blow to scientific progress, as these researchers are the ones pushing the boundaries of our knowledge. To get a clearer picture, I checked Ground News, a platform that aggregates articles from across the political spectrum. Left-leaning outlets emphasize the criticism of NASA's budget cuts, while right-leaning ones often frame the departures as early retirements. This contrast highlights the importance of seeking out multiple perspectives to understand complex issues. If you're curious about staying informed, check out Ground News for a balanced view. It's a great way to spot bias and get the full story. Let's zoom out for a moment and consider the grand choreography of the universe. The early universe was a stage where matter and energy performed a wild, chaotic dance. Galaxies weren't just forming, they were colliding, merging, and sparking new stars in a frenzy of creation. LID 568 and its fellow supermassive black holes were the conductors of this cosmic symphony, their gravitational pull shaping the galaxies around them. But what fueled this rapid growth? The discovery of LID 568's super-eddington feeding suggests that black holes could gorge on matter in bursts, accelerating their growth far beyond what we thought possible. This revelation forces us to rethink the tempo of the universe's early years, where the rules of physics bent under the weight of cosmic ambition. Imagine the sheer audacity of a universe that refuses to play by our rules. Doesn't that make you want to learn more? Drop a comment with your favorite cosmic phenomenon. The story of LID 568 is more than a tale of one black hole. It's a thread in the tapestry of time itself. Each observation from the JWST is like a page torn from the universe's ancient diary, revealing secrets written in light and gravity. But these pages are incomplete, and the gaps between them are filled with questions. Why do supermassive black holes appear so early, yet their intermediate cousins remain elusive? Could the dense, primordial conditions of the early universe have birthed black holes in ways we can't yet fathom? LID 568's defiance of the Eddington limit hints at a universe where exceptions are as important as the rules. As scientists pore over this data, they're not just studying black holes, they're piecing together the origin story of everything we see in the night sky. If this cosmic mystery has you hooked, share this video to spark a conversation with friends. Looking ahead, the journey to understand LID 568 and its implications is just beginning. The JWST, with its ability to peer into the universe's infancy, is rewriting our cosmic history books. But it's not alone. Future telescopes and missions will build on its legacy, probing deeper into the mysteries of black holes and galaxy formation. Scientists are already designing simulations to test whether super-eddington accretion could account for all supermassive black holes, or if direct collapse scenarios hold the key. Meanwhile, the search for intermediate black holes continues, with observatories scanning the skies for clues. The universe is a vast puzzle, and each discovery is a piece that brings us closer to the big picture. Let's keep the curiosity alive. Hit that subscribe button and join us for the next chapter in this cosmic adventure. The universe is a vast enigmatic tapestry, and LID 568 is just one thread in its grand design. As powerful as the JWST is, it hasn't cracked every mystery, not yet, but each observation, each rebellious black hole, brings us closer to understanding how the cosmos came to be. The early universe was a place of chaos and wonder, where galaxies formed faster than we thought possible, and black holes grew to sizes that defy our rules. LID 568 reminds us that the universe doesn't always play by our playbook, and that's what makes it so thrilling. So what's next? Scientists will continue to study LID 568 and other cosmic oddities, piecing together the clues to solve this galactic puzzle. Will we confirm the existence of direct collapse black holes? Will we find the missing intermediate black holes? Only time and more data will tell. For now, let's marvel at the universe's audacity, breaking limits and rewriting the rules. If this story has left you starry-eyed, drop a comment with your favorite cosmic mystery, and don't forget to subscribe for more journeys to the edge of the universe. Together, let's keep exploring the wonders that await.